Go. Here is the balloon demonstration.
Good morning, students. So today we're going to be doing a demonstration to start off our lesson. So here I have a candle, I have a balloon, and I have a lighter. So first what we're going to do is I will blow up the balloon and place the balloon over the fire. So when I blow into the balloon, remember I am blowing carbon dioxide out of my lungs, and that's going to put air particles inside of our balloon. The balloon is not going to have nothing in it. It will have air particles inside of the balloon. So I'll first blow it up. Then tie a knot. Okay, so one more time. What's in our balloon? Our balloon has air particles floating around inside of the balloon. And now I'm going to light up the candle. Alright, so now there is fire inside of our candle, and I'm going to be placing the balloon over the fire. It's not going to be touching the fire, but it will just be placed over the fire, and we are going to observe and see what happens. And again, some of you might already have some predictions or best guesses on what might occur, but we'll watch and see what happens. One more time to remind you all, the balloon has air particles floating around. Now let's see what happens when I place this balloon over the fire. Oh, let me drop. Here we go. Ready? Alright, so some of you might have predicted or guessed that the balloon was going to pop. And now through this lesson, we're going to find out why did the balloon pop? What made the balloon pop in this scenario? That's the question that we're going to try to answer by looking at other kinds of demos and other simulations that we'll see online. Thanks for watching.
Alright, so just now you watched the balloon demonstration, and the guiding question is, why does the balloon pop when placed above fire? So your homework for today will be to type up your response to this question and turn it into me. The rest of today's slides will help you figure out the correct answer to this question. So moving on, next slide. Number 2, now it says click this link to view a simulation and learn about how thermal energy transfer changes how particles move and the temperature. So I'm going to go ahead and click on this link, and it opens up a new tab. Now here I'm going to press start, and the heat is now on. So this lamp is transferring thermal energy. It's giving thermal energy to our beaker. And here's our thermometer, and you can see that the temperature will soon start to change. And these are the particles inside of our beaker. Now, as we keep waiting, you might notice that these water molecules are starting to move a little faster. They're jiggling around a little bit more. And as more and more time passes, we're going to see what else happens to these particles. Alright, so about a minute has passed, and you can see that these particles are starting to move around more. And as they gain more thermal energy, you can say that these particles have increased their kinetic energy. Their kinetic energy is going up, they are moving faster. Now, as they continue to move faster, if we wait longer and longer, because temperature measures the average kinetic energy of these particles, if we wait long enough, the temperature should also increase because the particles are moving faster. I'll give it maybe 30 more seconds and then we can move on. Alright, so telling you one more time, thermal energy is transferring from this lamp to our water. The water particles are moving faster and faster with more thermal energy, because remember, heat makes particles gain kinetic energy. They move around faster. And later on, this thermometer, the temperature should go up if we waited longer. But I'm going to go ahead and press pause and return to our slides. Alright, so now going back to our slides, we just viewed our online simulation, and now I'm going to have you watch this other demonstration.
Alright students, so you first watched the demonstration with the balloon, and we saw how when we place the balloon over fire, the balloon will pop. And we're trying to answer the question of why did the balloon pop when it was placed over fire. So to help us answer that question, you looked at an online simulation where we turned on the heat lamp on the computer, and with the lamp radiating thermal energy to the beaker with the water in it, you saw how the particles started to move a lot faster, and as the particles were moving faster, their temperature was increasing. So you notice that when thermal energy is added to the particles will move around faster. And the vocabulary word that we use to describe that is that the particles have more kinetic energy. They are moving faster. Now for our third demonstration, here I have a beaker of cold water, and over here I'm going to put in hot water from my kettle, and we're going to observe and see what happens when I put food coloring into each beaker. So for the cold water beaker, I'm going to put in 2 drops of blue food coloring, and for the beaker with the hot water, I'm going to put 2 drops of red food coloring at the same time, and our job is to observe and see what happens to the food coloring for each beaker. So I'll go ahead and pour my hot water. Again, you can tell that it's hot, it's steaming. So I'll pour the same amount as the cold water. Alright, so now I'm going to pour 2 drops of red food coloring into the hot water beaker and 2 drops of blue food coloring into the cold water beaker, and you're going to observe and see what happens. So let's try to do it at the same time. Here's the first drop, and then here's the second drop. So I'll go ahead and put this white paper up so you can see it better. Please observe what's happening to the food coloring. Alright, so I'm going to go ahead and describe my observations. So what I see right now is the food coloring from the blue in the cold water beaker is not really spreading around that fast. The food coloring inside the cold water beaker is not spreading around much. However, the red food coloring in the beaker with the hot water, it's already spreading around a lot, and it looks like it's dispersed into our water very quickly. Now the question is why? Why is that happening? Well, remember, inside of our beakers we have water particles, and you learned that in colder temperatures, the particles move around a lot more slowly. They move around slower, so they have less kinetic energy. While the water particles in the hot water, because it's very, very hot, the water particles are going to move a lot faster. They have more kinetic energy. So imagine when I put in a drop of food coloring into the cold water, because the water particles are moving around more slowly, the food coloring is going to spread around more slowly. However, in the hot water beaker, because the water particles are moving around with so much kinetic energy, they have so much energy and they're moving around very, very rapidly, very quickly, the drop of red food coloring is going to spread around that much more quickly because there's more kinetic energy. The particles have more kinetic energy in the hot water. Alright, so hopefully that helps you with your prediction or your answer to the question, why did the balloon pop when placed over the fire? You should know that the particles in higher temperatures are moving around more quickly. They have more kinetic energy than in the colder temperatures. Alright, thanks for watching this one.
Alright, moving on to the next slide. one moment.
About 5 minutes, and I want to bring your attention back to our beakers. So here you can see that the food coloring in the hot beaker has already dissolved and mixed in with that water. That shows to us that the water particles in higher temperatures, in hotter temperatures, are moving around a lot faster. They have more kinetic energy. So imagine the water particles in this one are moving around rapidly, they're spreading around very quickly, and they're allowing that red food coloring to mix in well with that water. However, in colder temperatures, water particles in cooler temperatures move around more slowly. They have less kinetic energy. They don't move around as fast. So you can see that the blue food coloring is still taking time to mix in and dissolve with the water because the particles are moving with less kinetic energy.
Alright, so for this video, I'm gonna fast forward. So this person has freezing cold nitrogen in this container over here, and he's gonna blow up this balloon and put it over this bucket. So I'll go ahead and full screen and you can watch him do this demonstration.
Go a little bigger than that. Do a little bit more. Okay. Let's tie it off here. Okay, so we have our nice red balloon here, blown up, and I'm gonna set that on this blue container. And in this beaker here, in this dewar, I have liquid nitrogen. Nitrogen is a very common substance. It makes up the majority of the air in our atmosphere. In its liquid form, it is very, very cold. The boiling point of liquid nitrogen is minus 196 degrees Celsius. So minus 196 degrees. And it's very, very cold. And you can see a little bit of vapor coming off here. I'm going to pour this gently onto the balloon. And in a second, we'll see some of the liquid come out. Oh, there's a little bit of the liquid. What's going to happen as I pour it onto the balloon, it's going to chill the balloon. It's going to start to cool the gas inside the balloon. And as that gas cools, since the temperature goes down, the volume of gas inside that balloon is also going to decrease. So the balloon contracts. I'm going to pour quite a bit of liquid nitrogen on here to make sure it's pretty far down. Makes a nice crinkling sound too as we do this. All right. So we've contracted the balloon, we've shrunk it down pretty far. Now I'm going to reach in here with a pair of tongs and pull out our shrunken balloon.
Alright, so this video is the opposite of what you saw with the balloon over the fire. So in this case, this person put freezing cold nitrogen liquid on top of the balloon, and what happened to the balloon? It began to shrink. And why do you think that is? Well, we learned that when the temperature drops, when thermal energy is removed, when heat is lost from the particles inside the balloon, well, then the particles are going to start to move slower. And as they move slower and slower, they're not going to take up that much space. And that is why the balloon starts to shrink, because the air particles in the balloon, since they're losing thermal energy, they start to move around less and less and less and take up less volume, take up less space.
And as soon as I start pulling it out, it starts warming up. And you can see, I'm going to set it here on the table. As it's warming up, it's going to start expanding. The gas inside warms up and expands. Also makes a nice sound as it's warming back up. And if we give it a moment or two, it will be back to approximately its original size. And there we go. We have shrunk and re-expanded a balloon. Thank you very much for watching. My name is Ken.
Alright, and then now when he took the balloon out of the freezing cold nitrogen, the balloon the air particles inside the balloon started to gain thermal energy again, and they start to move around more quickly. They start to take up more space, and this causes the balloon to expand, to grow back into its original size. All right, we have